So today's topic of discussion is collisions. Collision. What is a collision? In physics, we define collision as the event where two bodies, which were initially moving with two different velocities, come together, interact with each other, and in the process change each other's momentum, velocity and hence momentum, and finally they move with two different velocities, different from their initial velocities. Okay, so this is what we call as collision. Now, going into the details, what we have here is there is a mass m1 which is initially moving with a velocity u1, initial velocity. Another mass m2 which is moving with initial velocity u2. Now, if they have to come together, if they have to collide, understand that u1 should be greater than u2. m1 should be moving faster than m2. Only then m1 will approach m2, and in some time they will come together, they will come in physical contact with each other, and when they come in physical contact they exert forces on each other. The nature of the force will be that of normal reaction. They'll exert normal force because of the physical contact that they are having. And in this process, if let us say m1 exerts a force F on the mass m2, then by Newton's third law we can say that m2 exerts the same force back on m1. So that if we consider these two bodies, these two colliding bodies as one single system, we can say that the forces are only internal in nature. There is no external force acting on the system. Okay, and if there is no external force acting, can we say that the total momentum of the system will remain conserved? It will remain a constant. This we understand now from the previous discussion, the discussion that we had on the law of conservation of momentum, right? We know that if there is no external force on the system, then that the total momentum of that system will remain conserved. However, see that individually both the masses are experiencing some force, and hence they will undergo some change in momentum. So the initial velocity u1 will change to a final velocity v1, and the initial velocity u2 will change to a final velocity v2 by the time the two bodies once again separate from each other and move independently. Okay, so this is the basic understanding of collisions. Understand that this force that acts between the two bodies, depending upon the extent of contact that the two bodies have, which we shall discuss in detail a little later when we discuss types of collisions, we shall see that this force F is not actually a constant force. It keeps on varying with time. As the collision happens, as the bodies come in contact with each other, there is some time interval for which the bodies are in contact, during which this force F will vary depending upon how much strong the connection or the impact between the bodies is. The other thing is, generally collisions take place for a very short duration of time, a duration which is as small as, let's say, a 0.1 second or so, okay, fraction of a second. During this small time, any force that acts on a body is called an impulsive force. So these forces that are coming in between and acting on the two bodies, both are having the same value F. These are impulsive forces by nature. They act for a very short duration of time. The result that they produce though is the same. They produce a change in momentum in the bodies, right? So the velocities of the body change, but they act for a very short duration of time. So impulsive forces, as they are called, we shall study them like impulsive forces as such. When they create a change in momentum, that is studied in the form of impulse, which we shall see in the upcoming topics. But for now, we shall discuss the topic of collision only considering simply the forces acting between the bodies. Not just that, knowing that the external force is zero, our job becomes even simpler when we know that the total momentum of the system will remain always conserved in a collision. If there could be some special cases, some special scenarios where there are external forces, but otherwise in a collision, if you see that there is no external force coming and acting on the system, we can always say that the net momentum of the system will remain conserved, which in this case would mean that m1 u1 plus m2 u2 will be equal to m1 v1 plus m2 v2. Understand that this is the equation that we get by the conservation of momentum which will always be valid. We can call it equation number 1. Why so? Because understand that if we know the masses of the two bodies and the initial velocities of the two bodies, u1 and u2, and if we want to find out the final velocities of the two bodies after collision, v1 and v2, understand that v1 and v2 both are our variables. We need to find out both these values. Whereas this equation help us find out the relation between v1 and v2. We can't really get both the values of v1 and v2. We can just get a relation, because for two variables we need at least two equations to find both the values, right? So this equation then, the law of conservation of momentum, serves as the first equation to help us get the values of v1 and v2. That's why equation number 1. Okay. So the important thing that we have understood just now is that conservation of momentum is always valid in case of collisions, except for a few exceptions which we shall see very soon, as the external force acting on the system is 0. Okay. Now, this is just one equation that we have obtained, right? But we require one more equation in order to be able to find out v1 and v2. Where will that other equation come from? We say that the other equation we can obtain if we know the type of collision that this is, which essentially depends upon the nature of the two colliding bodies, the nature of the material of which they are formed. Okay, that helps us get the second equation. And when we try to get that, we study this, like the type of collisions, as the next topic, where we shall see that in terms of the energies associated with the system, we have three basic type of collisions. So types of collisions then become our next topic of discussion. The first type is what we call as a perfectly elastic collision, or sometimes we simply call it as a elastic collision. Perfectly elastic collision. What is a perfectly elastic collision? We say that in simple language, a perfectly elastic collision is the one in which the total kinetic energy of the system, kinetic energy of the two colliding bodies, remains conserved. So what does that mean? Mathematically, does that mean that m1 half m1 u1 squared plus half m2 u2 squared, this is the total kinetic energy before collision, this should be equal to half m1 v1 squared plus half m2 v2 squared, right? So can we say this equation that we have obtained just now can serve as the second equation to use with the first equation, so that we can find out both v1 and v2, right? So as soon as we know that the collision is perfectly elastic, we can use the law of conservation of energy and solve it along with the first equation to get both v1 and v2, right? So we need not know anything else here if we know the type of collision, if it is perfectly elastic. Now, what makes a collision perfectly elastic? Let's get into the details, the nature of the perfectly elastic collision a little bit more, which will help us understand the other types of collisions also better. So a perfectly elastic collision is something in which the two colliding bodies, they behave like perfectly elastic bodies. What do we mean by that? Understand that when the two bodies which are about to collide, they come together, let's say this is m1 moving with u1 and m2 which is moving with u2, we know that they will collide if u1 is greater than u2. That means m1 comes from behind and approaches m2, comes closer to m2 with time. When they come in contact with each other, like this, what they do is they exert impact forces on each other. m1 exerts an impact force F on m2 towards right, and m2 exerts the same impact force F on m1 towards left. In the process of this force that comes in between the two bodies get deformed. Their shape changes, so that if I have to just show you a rough figure of how the two bodies which are in contact with each other look like, they look like this. This particular portion gets deformed in its shape. And this deformation can be thought of as a deformation of a spring. Okay, the two bodies press each other, so that they get deformed. And just as when a spring gets compressed, deformed, it tries to come back to its original state by exerting opposite forces. What happens is these bodies, because they've got deformed, they try to reform their shapes by exerting these forces, due to which they again come out of each other's contact, and finally the velocities that they gain will be corresponding to the original shape having been acquired by the body, so that when they come out after the collision gets over, this is the process of collision when the two are in contact with each other. Once they separate away from each other and they again come out, their velocities v1 and v2 will be such that their kinetic energies initially and finally are the same, and the shape of the bodies will be exactly the same as their original shape, so that we say that there is no loss of energy. There is no loss of energy that takes place in the process of deformation, because all the deformation that took place, it went away. It was reformed, okay, completely. There is no deformation left in the two bodies. Okay, so from there we understand that in case of a perfectly elastic collision where the two bodies behave exactly like spring type bodies, they completely reform themselves after getting deformed in the process of collision and come out with final velocities corresponding to no change in final kinetic energy. Understand that because the bodies are behaving like springs, and we know that spring force is a conservative force, it does not dissipate any energy, right? So this is the reason why we say that in this case also no energy will be lost by the bodies. There's another way in which we can understand the process of a perfectly elastic collision, which is by taking the two bodies coming together through a spring connected in between them. So for example, let's say this is M1 and this is M2. M1 is moving with U1, M2 is moving with U2, and there is a spring that is connected over here with, let us say, M2. The front portion of the spring is connected with the M2 and the other end of the spring is open, which will get connected with M1 as M1 approaches M2. Do you understand? As M1 approaches M2, initially when it comes in contact with this point, because M1 is moving faster with a velocity U1, M1 is moving, right? So can we say in this case, as M1 comes and touches the spring, this end of the spring over here, understand that this end of the spring will move with a velocity of m1, which is u1. As m1 is moving with u1, this point of the spring will move to the right with u1, whereas this point of the spring, the right end of the spring, will be moving along with m2 with the speed of m2, which is u2. So this point is moving with u2. So if the hind point is moving with u1 and the front point of the spring is moving with u2, and we know that u1 is greater than u2, that means the rear end of the spring is moving faster than the front end. What do you think will be the result of this? The result of this will be that the spring will get compressed in the process, isn't it? m1 is moving faster than m2, m1 will compress the spring, m2 is opening the spring, the compression is higher than the expansion, so the spring overall will get compressed. So after some time the state of the spring will be like this. It will be in a compressed state, right? Understand that both the bodies are still moving. Both of them are moving with certain velocities. So as the spring gets compressed, do you understand that in order to decompress itself, it will exert restoring forces on the two balls in this direction? So if the spring is, let's say, compressed by x, can we say kx is the force that the spring will exert in the forward direction on m2 and in the backward direction on m1? What will be the result of this force coming from the spring and acting on the two bodies? Understand that on m2, this force, when it acts in the forward direction, it will accelerate m2. It will increase the velocity of m2. m2 was initially moving slower, right? Now m2 starts accelerating. Whereas the same force kx, which is acting in the leftward direction on m1, will deaccelerate m1. It will slow down the body m1. So m1, which was initially moving with a greater speed u1, will now slow down, right? So m1 initially moving faster, m2 moving slower. Because of the spring force, now m2 accelerates and m1 deaccelerates. What do you think will be the result of this? The result will be that a point will come when both the ends of the spring, which means both the bodies, colliding bodies, will be at a certain point will be moving with same velocities. Let's call that velocity v. Okay? Can we say when u1 decreases down to v and u2 increases to v, at that moment both the ends of the spring will be moving with the same velocities? If they are moving with same velocities, that means the spring will no more compress now. Till now the spring was getting compressed because m1 was moving faster than m2. At this point the spring will have, if you can understand this will be the state of maximum compression of the spring. Why maximum compression? Because still here the spring was getting compressed continuously. At this moment it stopped getting compressed further, whereas after this time the spring will now open up. Why will it open up? It will open up because the forces kx are still acting on the two bodies. The spring is still compressed, understand. The two forces kx are still acting on the bodies, and as a result m2 is further going to accelerate and m1 is further going to deaccelerate. So from the common velocity that they have acquired just now, from here now as the time proceeds, m2 will now move faster, go on moving faster and faster, and m1 will further slow down. So that m1 will now, after this point, m1 will have a velocity which will become lesser and lesser than the velocity of m2, and the m2's velocity will keep on increasing. Okay, so understand that this is one important state in the process of collision where the two bodies under the state of maximum compression in the spring will have the same velocity. After which m2 will move faster, m1 will move slower, and this will continue to happen as the spring opens up and reaches once again its original length. So by the time the spring once again reaches its original length, do we understand that the bodies m1 and m2 would have acquired new velocities v1 and v2, where in general now v2 will be greater than v1? Can we say that? Right? m2 will be now moving faster. And it is at this state when the spring once again comes in its natural length. If it comes in its natural length, this means that now the spring does not exert any further force. The force of interaction between the two bodies ceases to exist. The two bodies will now just separate from each other. This point will once again get detached from the mass m1, and the two bodies will now finally move with final velocities v1 and v2, which will then becomes the final velocities of the bodies after the collision. Okay, so in this case understand that it is only because of the spring force coming into picture and doing some work in the process, because there is a spring force, right, and the bodies are undergoing a change because of that. Spring force is the only force acting between the bodies, and we know by nature spring force is a conservative force, right? So do we understand, because this is the case, can we say that there is no loss of energy in the body in this process, right? So can we say that the total energy of the system of the two bodies as well as the spring will remain conserved at any point in time? Initially, the energy of the system was only kinetic. The two bodies had only kinetic energies. Spring was not compressed, so no spring potential energy. Finally, when the collision completes, then also the two bodies have only kinetic energies. The spring is once again in its original length, so no spring potential energy. So can we say by law of conservation of energy, the initial kinetic energy of the system should be equal to the final kinetic energy of the system? Can we say that, right? So this is what makes us understand how in a perfectly elastic collision, the total energy, the total kinetic energy of the system of colliding bodies remains conserved. Okay. Okay, so this is about a perfectly elastic collision. We are going to discuss the mathematics of perfectly elastic collision in further detail in the upcoming video. For now, let us move on to the next type of collision. The next type of collision is called a perfectly inelastic collision. Perfectly inelastic collision. What is a perfectly inelastic collision? Sometimes we simply call it as inelastic collision also. An inelastic collision is the one where the two bodies are made up of such material which is absolutely non-elastic. Non-elastic basically means that once the bodies have got deformed during the course of collision, once they have suffered some deformation, now there is no tendency in the bodies to undergo a reformation. They would not try to change their state of deformation because there is no elasticity in the material itself. It's not like spring. It's like I have to give you an example of a inelastic material, it would be like clay. Clay is one material which if you deform it in any way, it will remain in that deformed state, isn't it? So the two bodies are like clay. If they come together, they press each other, they deform each other, and then they stay like that. Okay? So that in case of a perfectly inelastic collision, the two bodies, once they have suffered some deformation, they stay with that deformation. They have no tendency to further separate from each other, and they move like this itself after collision. So after collision, in case of a perfectly inelastic collision, we say that after the collision is complete, the two bodies do not separate from each other. Rather, the two bodies stick to each other after the collision and they move together with one common velocity v. Okay? So we can say that the two bodies stick to each other. Stick to each other and move with a common velocity. Okay, which here we have written as v. So if that is the case, understand that the law of conservation of momentum is still valid. Why so? Because when the bodies came together to interact, the forces of interaction were still internal. There was no external force. So we can still say that conservation of momentum is still valid, which means that we can still write m1u1 plus m2u2. If we assume that initially the bodies were moving with u1 and u2, these are the initial momenta together. This should be equal to the final momentum of this system of two bodies, which do we understand? We can write them like this. Now both the bodies move together with a common velocity, so the common momentum of, like the total momentum of the two bodies will now be m1 plus m2 times v. So from here now, this is not an arrow sign, this is actually an equality sign over here. We can just put an equality sign. This is equal to this, right? Do we see that it is from this one single equation this time that we can get the value of v, the final velocity of the two bodies? m1u1 plus m2u2 over m1 plus m2. So just one single equation this time is helping us get the final velocity of the system which underwent a collision. Do you also observe that this expression we have already studied? Isn't this the expression for the velocity of center of mass? So this final velocity with which the two bodies will move will be nothing but the velocity of center of mass itself. Okay, so in a perfectly inelastic collision, we say that the two bodies that undergo a collision, after collision they stick to each other and they move together with a common velocity which is the same as the velocity of center of mass of the system of two bodies. Okay, an important result to remember. But understand that in case of a perfectly inelastic collision, a lot of energy gets lost. Why? Because of this deformation happening and no reformation happening, the energy will be lost in this process of deformation. And in fact, the loss of energy in case of a perfectly inelastic collision is the highest amongst all the type of collisions we discuss here, which we can find out. We can find out the loss of kinetic energy of the system here by, do we understand how do we get the loss? Can we say the loss will be nothing but the initial kinetic energy of the system minus the final kinetic energy of the system? Can we say that? Because we know that the final kinetic energy is less than the initial kinetic energy, isn't it? Now if we just try to get the expression for this, initial kinetic energy is nothing but half m1u1 squared plus half m2u2 squared minus the final kinetic energy of the system would be half into, now since they are moving together, I can take both the masses together as m1 plus m2, and then this v squared, this v that we have obtained here, we can substitute this value over here and get the loss of kinetic energy. and you will see that there is a small mathematics that goes into this. It can be easily proved that this expression when solved gives us an expression which we can directly use into questions. Half m1 m2 by m1 plus m2 into v1 minus v2 whole squared is what we get as delta Ke, the loss of kinetic energy of this two particle system in case of a perfectly inelastic collision. We shall see this later, that this particular term is given a special name. We call as the reduced mass of the system, m1 m2 by m1 plus m2, and v1 minus v2, understand, is nothing but the relative velocity. I'm sorry, this is going to be u1 minus u2. V is going to be common. This will be u1 minus u2, the initial velocities, u1 minus u2 whole squared. So relative velocity with which the two bodies were moving initially. Okay, so this is in terms of u1 and u2. So relative velocity of the body. So this expression, if you can use it directly into questions. Otherwise, you have the basic expression always with you, the basic definition of loss of kinetic energy. You can always use to solve questions. Okay. So this is about a perfectly inelastic collision. Just to revise, in a perfectly inelastic collision, because there is no elasticity in the system, there is no tendency to reform the system once deformation has taken place. So no separation between the bodies after collision. The two bodies stick to each other and move together with their common velocity of center of mass. Now we come to the third type of collision, which we call as a partially elastic collision. Partially elastic collision. So as the name suggests, partially elastic means which is neither perfectly elastic nor perfectly inelastic. It lies between the two, right? Now, depending upon, once again, the nature of the material of the two colliding bodies, the amount of elasticity can be varying. A collision could be more elastic and less inelastic, and it could be less elastic and more inelastic. That depends upon the nature of the material, which can have any range of values. I hope you understand this. So the partiality of the collision, the partial elasticity can be of any extent, due to which we say that in case of a partially elastic collision, we define a new term through which we are able to get our second equation. Understand that the first equation will still be the same. If we have the two colliding bodies of masses m1 and m2 moving initially with u1 and u2, undergoing a collision, and after the collision moving with new velocities v1 and v2, let's say this is v1 and this is v2. So this time once again we require two equations to solve for v1 and v2, out of which one equation we get from conservation of momentum itself. The momentum of the two bodies will still be conserved, right? So this would give us m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. This serves as the first equation. Where does the second equation come from? It comes from understanding how much elastic the collision is or how inelastic the collision is, which comes from a new term now that we define here, which we call as the coefficient of restitution. Coefficient of restitution, a new term to be defined here. We denote this term with the letter small e. Coefficient of restitution. E tells us about the extent of elasticity of the collision, how elastic the collision is. And by definition, we say that E is, we'll just define it once and then we'll understand what do we mean by the terms. E is the velocity of separation after collision divided by the velocity of approach before collision. Now let us see what these terms are. What do they mean? Okay. So when these two bodies are moving initially before the collision, Do you understand it is because m1 is approaching m2 that the two bodies collide, the collision between them takes place, because m1 was approaching m2, it was coming closer to m2 with time. With what velocity is m1 coming closer to m2 before collision? That's the velocity of approach. Okay, so understand that since u1 is greater than u2, m1 is moving faster, m2 is moving slower, we say that the velocity with which m1 approaches m2 is the relative velocity with which m1 moves closer to m2, considering m2 at rest. Okay, considering m2 at rest, with what velocity will m1 move closer to m2? Can we say that will be nothing but the relative velocity of m1 with respect to m2, which by definition will be u1 minus u2, right? So we say that the velocity of approach before collision, of course, because it is before collision that the two bodies are approaching each other, this comes out to be nothing but the relative velocity with which m1 is coming closer to m2, which in this case will be u1 minus u2. Okay, we can also call it the relative velocity of m1 with respect to m2. After collision, we know that the two bodies move away from each other, because in general we have seen that v2 becomes greater than v1, right? So m2 moves away from m1 after the collision. So if m2 is moving away from m1, does that mean that m1 and m2 are getting separated? With time, the separation between m1 and m2 increases. So with what velocity does m2 separate from m1? How do we calculate that? We say that the velocity of separation is nothing but the velocity of m2 with respect to m1, considering m1 at rest. With what velocity is m2 moving away from it? That will be nothing but the velocity of separation. So velocity of separation, which we now understand, is nothing but the relative velocity of m2 with respect to m1. Can we say it will be nothing but v2 minus v1? Yes. So this is the velocity of separation after collision. Understand that separation is happening after collision only. So we can define velocity of separation only after collision. Okay. So then if we use these values here in the definition of E, the coefficient of restitution, do we understand that E becomes velocity of separation after collision, that means v2 minus v1, over velocity of approach before collision, which is u1 minus u2. So this becomes our mathematical definition of E, the coefficient of restitution, which we can use into questions directly. This is the theoretical definition. Remember this always. Understand that these values that we have got and their signs are under the assumption that all the four values u1, u2, v1 and v2 are all pointing in the same direction, towards right. Sometimes this may not be the case. Sometimes it might happen that after collision the two bodies are moving in opposite directions. v1 and v2 are in the opposite direction. So in that case we need to change the sign here accordingly. Okay, so this will happen if you remember the basic definition well. So remember this basic definition properly so that you don't make any mistake in getting the value of E, the coefficient of restitution. It is found that in case of partially elastic collision, for partially elastic collisions, the value of E is within a certain range. What is that range? E always lies strictly between 0 and 1. It can take any value above 0 and any value below 1. So understand that depending upon the various values that E can take, our collision will be either more elastic or less elastic, like that. So it can take all range of values corresponding to different types of materials of the colliding bodies. Also, know that as a special case, as we have discussed a perfectly elastic collision, for a perfectly elastic collision, and we shall be proving this in the upcoming video where we discuss perfectly elastic collisions in detail. For a perfectly elastic collision, we can prove that E is equal to 1. Whereas for a perfectly inelastic collision, the value of E is 0. This we can understand here itself. What do we mean by E is equal to 0? E is equal to 0 from this definition means velocity of separation after collision is 0. Velocity of separation after collision is 0 means that the two bodies are not separating away after collision. The two bodies are not separating away after collision means that the two bodies are moving together. Doesn't that what we mean by no separation happening between the bodies after collision? Right? So it is true from what we have understood about perfectly elastic collisions itself that in case of a perfectly elastic collision, because there is no separation after collision, the two bodies move with one common velocity, there is no separation, and hence the coefficient of restitution would be 0. Okay, so these are some finer aspects, and as we work through questions, we'll get more comfortable with using all these definitions. So just for the sake of understanding how to apply this, let's take up a small example based upon a partially elastic collision and see how we use the definition of E there, the coefficient of restitution. So this question says that there is a block of mass m which is moving at a speed of v, and it collides with another block which is having a mass of 2m, which is initially at rest. So u1 is given to be v, whereas u2 is 0. Okay. Now after collision, it is given that the lighter block comes to rest. The mass m has its final velocity 0. We are supposed to find out the coefficient of restitution of this particular collision. So what is not given to us is the final velocity of the bigger mass, which I hope you all understand we can find out first. And then once we get the velocity, then we can use the definition of E, coefficient of restitution, to find it out, to find out the value of E. Okay, this is the question. So what do we do to find out E? We first use our equation for conservation of momentum to find out the value of V2, the velocity of the second mass, right? Do we understand that by conservation of momentum, we will get the initial momentum for the first body, it is m into v. For the second body, the initial momentum is 0. 2m into 0 is 0, is equal to, finally after the collision, the first mass comes to rest, so its momentum will become 0, plus the momentum of the second mass will be 2m times v2. From this equation, we see that v2 comes out to be v by 2, right? So we have got the value of the second mass, velocity of the second mass. Now let us use the definition of E. So by definition now, E is, what is E? The velocity of separation after collision, v2 minus v1, over the velocity of approach before collision, u1 minus u2. Substitute all the values. v2 is v by 2, v1 is 0, divided by u1 is v minus u2 is 0. So when we solve this, we see that the value of E comes out to be 1 by 2. So know the basic definition, use it to get your final answer. The next topic we shall now discuss about perfectly elastic collisions in detail. We shall see that there are some special cases related to perfectly elastic collisions that we need to know in order to solve our questions in a more confident way, in a way in which we take less time and solve the questions confidently. So perfectly elastic collisions in the next topic.